So in this session, let's talk about what we call isotopes. Now, let's consider isotopes. Let's say we have twins here. Now, there's one thing that we know about twins. We all know that twins look the same. And I'm talking about identical twins. Okay? We have this twin here and this one. They are the same. In other words, they have the same face, they have the same face, they are born of the same parents, they are of the same clan, everything about them is the same. But there is this small difference between them. This one is small than this one. This one is bigger. So if you're having this kind of condition whereby you're having twins, they look the same, they have the same smile, same face, same clothes, same parents, same everything, but then one of the twins is bigger than the other. This kind of condition is what we are calling that these two are isotopes. That is if you are to talk about it in this context of, what is it called? In this context, we're talking about here in physics. So by saying this, I mean to say that isotopes are atoms. In this case, the atoms are the people, the twins, of the same element. Atoms of the same element, meaning that they look the same. They are born of the same parent, same whatever. They are atoms of the same element having the same atomic numbers. It's the same atomic numbers that distinguishes them to be the same of the same parent, but different mass numbers, meaning that they are the same atomic number but different mass numbers. They have different weights. One is bigger than the other, one is heavier than the other. Okay, so that is what we mean. For example, let me give an example. We have examples here. We have carbon, we have chlorine, we have rhenium. What I'm trying to say is that can have chlorine here and another chlorine here, meaning that these are twins. They are the same. They have the same atomic number, but they weigh differently. This one is heavy. His mass number, chlorine, one of them is 35 right here, and the other's mass is different from that. The other one is lighter, is heavier, 37. So from here you can see that they have the same mass number. I mean same atomic number, but their mass numbers are different. If you look at that, their mass numbers are different mass numbers. So when they have different mass numbers, yet their atomic numbers are the same, those are what we call isotopes. Okay, and so there's just a few examples. We have carbon 12, we have carbon 13 and carbon 14, then we have chlorine 35 and chlorine 37, then we have uranium 35 and also another uranium here called 35. So the issue here is it's the same element, that's why it's having the same number of protons, or call it the atomic number, but the mass numbers are just different. That's what we call isotopes, and their existence is what we call isotropy. Or in other words, what isotropy means is the existence of atoms of the same element, but with the same atomic number, but different mass numbers. That is isotropy. Okay, so we've explained isotropy. Let's look at this question. Describe the composition of the following nucleides. Now remember we said that nucleides, this word here, remember when we are drawing our atom before, that this is the nucleus. The nucleus has the number of protons and the number of neutrons here. Then the electrons are around in the energy shells. And remember we said that the particles that are in the nucleus are sometimes called nuclides. So when they say describe the composition of the following nuclides, they are asking you to describe how many protons and how many neutrons are in that. So if you look at this one, remember we said that this is 88 atomic number. We said atomic number is the same as the number of protons. So from here, we are able to tell that the number of protons is 88. So the number of protons is 88. So what about the number of neutrons? Remember up here, the top number, 228, this top number represents the number of neutrons. I mean the mass number, this is the mass number. This top number is the mass number. And you know the mass number to be the number of protons plus the number of neutrons. But remember, we already know the number of protons, they are 88. Okay, so it means that if we have the number of protons as 88, then you need to plus the number of neutrons, which you should not know, is equal to the mass number, which is 228. So in other words, here it is, let me write it here correctly, it's 228 is going to be equal to 88 plus the number of neutrons. 228 meaning the mass number is equal to the number of protons, which is 88 plus the number of neutrons. So we find the value of n, which happens to be the number of neutrons. So the number of neutrons in that case is going to be 228 minus 88, and the answer we get there is 140. So after getting 140, remember the question says describe the composition of the following nuclides. So the composition here, we shall simply come and say that for Roman 1, that the atom has 88 protons and 140 neutrons. As simple as that. So that's how these questions want you to answer them. It's just a matter of finding the number of protons and the number of neutrons, and you're good to go. So it's the same thing you do with Roman 2 and the same thing you do with Roman 3. Just using that to find the number of protons and neutrons that are found in those nuclides. And so that's it. We have talked about isotopes.